In this lesson, we'll derive the equation for calculating the magnitude of the hydrostatic force on a plane surface. Here we have a rectangular fish tank filled with water to a depth d. In order to determine whether the fish tank walls can support that much water without breaking, we would need to know the total force exerted on the walls. First, we will determine the resultant force along the bottom wall. The tank is surrounded on all sides by the atmosphere, which has a pressure Pa. On the underside of the bottom wall, which is exposed to the atmosphere, the pressure force is Pa times the area of the bottom wall, and this force points upward. Inside the tank, the pressure force increases as one descends through the water, reaching a maximum at the bottom of the tank. The absolute pressure at depth d is the atmospheric pressure plus the specific weight of the water times the depth. This creates a downward force on the wall equal to Pa plus gamma d times the area of the bottom wall. If we examine just the fluid pressure forces acting along the bottom wall, the resultant force is Pa times the area of the bottom wall minus the quantity Pa plus gamma d times the area of the bottom wall. The atmospheric pressure terms cancel out, and we are left with negative gamma times d times the area. This means that the resultant force points downward with a magnitude of gamma times d times the area. Finding the resultant pressure force along the bottom wall was relatively easy because the pressure is constant along the entire wall. This is not the case for the side walls. The pressure along the exterior of the side walls is Pa, and the related pressure force is Pa times the area of the side wall. However, on the interior of the side walls, the pressure increases linearly with depth. At a depth h, the pressure is the atmospheric pressure plus gamma h. We want to determine the magnitude of the resultant force caused by the fluid pressure on the side walls. Here is a different tank. This tank is open to the atmosphere and partially filled with a liquid of specific weight gamma. We are going to examine a section of the flat wall that's highlighted in pink, which has an arbitrary shape and which is oriented at an arbitrary angle theta relative to the free surface. We set up a coordinate system where the x-coordinate comes out of the screen and is oriented along the free surface. The y-coordinate is oriented along the section of wall we wish to examine. We will need to examine some important points on the wall, so we rotate the surface 90 degrees about the y-axis to get a better view. Point xy is the location of some arbitrary small area dA on the wall. dA is the area dx times dy and is at a depth h from the free surface. Point C is the centroid of the wall and is located at coordinates xc, yc. The depth of the centroid from the free surface is hc. The centroid is the geometric center of the wall, and the centroid and center of mass are the same if the density of the wall is constant. Point CP is the center of pressure, which is where the resultant force Fr acts. The coordinates of the center of pressure are labeled as xr, yr. The resultant force and center of pressure location produce an equivalent force and moment on the wall as the original fluid pressure field. In order to find the resultant force over the entire highlighted surface, we will start by examining the force at the location of dA. The small pressure force on the exterior of the wall at area dA, labeled dFx, is the atmospheric pressure Pa times the area dA. The small pressure force on the interior of the wall at area dA, which is labeled dFin, is the fluid pressure at dA times the area dA. The pressure at that depth is the atmospheric pressure plus gamma h. Using trigonometry, h can be rewritten as y times sine theta. The net force due to fluid pressure at dA is dF interior minus dF exterior. After plugging in the expressions for the two forces and eliminating Pa times dA, we obtain gamma times y sine theta times dA. To find the resultant force caused by fluid pressure on the entire wall, we integrate dF net along all points of the wall. We plug in the expression for dF net and pull gamma sine theta out of the integral because they are constant. The integral of y dA can be simplified if we recall the definition of a centroid. The y-coordinate of the centroid, yc, is the integral of y dA integrated over the entire surface divided by the entire surface area A. We now have an expression for the resultant force Fr. Fr is equal to gamma times sine theta times yc times the area. Yc times sine theta is equal to the depth of the centroid, hc, so we can rewrite the resultant force equation as gamma times hc times A. This form of the equation is often more convenient to use when solving fluid mechanics problems. Gamma hc is the pressure at the centroid, Pc, so we can further rewrite the resultant force equation as the pressure at the centroid Pc times the area A. These equations are valid for any flat surface in which the free surface of the liquid and the side of the tank are both exposed to the same pressure. In this case, they're both exposed to the atmospheric pressure. We are free to use either yc or hc to find the resultant force, and it's important to understand the difference between the two quantities. hc is the vertical distance from the free surface to the centroid, and yc is the distance from the free surface to the centroid as measured along the orientation of the wall. If the wall is oriented at an angle less than 90 degrees relative to the free surface, hc will be shorter than yc. If the wall is vertical and theta is 90 degrees, hc and yc will be the same distance, and in both cases the distance yr will be greater than yc. Although not proven in this video, if the tank is pressurized to a gauge pressure of P0, the equation for the resultant force would need to be modified to gamma sine theta yc plus P0 times the area A, which can be rewritten as gamma hc plus P0 times A.